I will talk about the code book, but in case you haven't read any of my books, I thought I'd start by just telling you a little bit about what I do and why I do it. My background's in physics, so I love science and I love technology and I love maths, but I now write about anything to do with science. So I've written a book about alternative medicine, a slightly offbeat topic for me, but I'm worried about alternative medicine. I think there's some risks and some dangers. Some alternative therapies do work, but it's potentially dangerous. So this book I wrote with a doctor called Edzard Ernst. I've written a book about pure mathematics, about Fermat's last theorem. I've written a book about the Simpsons and so on. And I write about these subjects because I want to get other people as interested in science and technology as I am. So this is the kind of stuff I do. I mentioned this book. Do I mention this book? I mentioned this book briefly. One of the things when I write these books for kind of the general public is I try and tell the stories of the scientists as well as the science. So I tell the human stories as well as explaining the science. And another of my books is the code book. And Sven explained that I talk about how cryptography has evolved over the centuries. You know, somebody makes a code, somebody breaks the code, somebody makes a better code, somebody breaks that code, and so on and so on. But rather than looking at the whole history, I thought I would look at the back of the book. At the back of the book, there was something called the Cypher Challenge. And the Cypher Challenge was a competition. There were 10 coded messages from 10 periods of history. Some of them, well, the early ones were very simple and very ancient, and the later ones were very modern and very difficult. And the idea was that children could break the early codes, but if you were really serious and you broke all the codes, then you could win £10,000, okay? And the competition was eventually won by some Swedish, they were actually jugglers in London on a conference, a juggling conference. But one was a computer scientist, one was a number theorist, one was a cryptanalyst, one was an electrical engineer, one was a computer scientist. They went back to Stockholm and they worked on these 10 codes and they won the money. They won the competition. And when I wrote the check, I tried to write it in code in the hope they wouldn't cash it, but they still were able to cash it. So they got their money. And these are the 10 codes they had to crack. So this is a 2,000-year-old code. This is a 1,000-year-old code. This is a 500-year-old code, 200-year-old, and so on, through to the First World War, Second World War, right up to the 70s and 80s. So this is the challenge that people had to crack. And I'm just going to look at some of these codes and explain to you how they were cracked and so on. This was the first stage, a very simple monoalphabetic substitution cipher. You replace every letter with a different letter. Now that code would have been unbreakable 2,000 years ago. But it was broken. The first document we have on cryptanalysis, the first code-breaking document we have, is this one here, by an Arabic mathematician called Al-Kindi, who was living and working in Baghdad. And this document was only found about 20 years ago in Istanbul. And in this document, what Al-Kindi says is that every letter has a frequency. So this is the frequency for English. I think in German, E is even more common. And Z's probably a bit more common. The distributions change, but for each language, the distribution is really distinct. And so if E is the most common letter in English, and X is the most common letter in the ciphertext, then you kind of know that X must be E, okay? So today, that's fairly obvious to us. But when Al-Kindi did it, when Al-Kindi worked it out, it was revolutionary. And it gave him and his compatriots a huge advantage in breaking the codes of their rivals. So that was first stage one. That was easy to even though that code was broken 1,000 years ago by Al-Kindi, it was still being used by Mary Queen of Scots about 500 years ago. She was a Catholic Queen of Scotland who wanted to become, she was also Queen of France briefly, and she wanted to become Queen of England. And she was a Catholic, and Elizabeth I at the time was a Protestant, and Elizabeth was scared that Mary would overthrow her and become queen. So Elizabeth put Mary in prison to keep her safe and locked away. But while she was in prison, she sent out these coded messages to people in Spain. And she was saying to the Spaniards, come and invade England, let's get rid of Elizabeth, make me queen, make me the rightful queen. Now, these letters were encrypted, but they were intercepted. They were given to Elizabeth's codebreakers. They pretty much follow a simple substitution cipher. Elizabeth's codebreakers were able to break the codes. It was clear that she was committing treason. She was put on trial for treason. She was found guilty and then executed. So you can see how important the making or the breaking of a code can be. It can be a matter of life and death in this situation. Let me jump forward in time. So stage 1 was easy. Stage 2 was easy. 3 and 4 are a bit tricky, but really most teenagers, I think, could do 3 and 4. 5 was the really tough one. 5 was the first one that really stopped people. In fact, nobody could break this code for 6 months. And stage 5 is what's known as a book cipher. And the way a book cipher works is you take a book and you number every letter in the book. 1 right through to the end. So it may be 1 million letters. You may have 1 million numbers next to each letter. And then what you do is, let's say my book is A Tale of Two Cities. It was the best of times, it was the worst of times. So I'm numbering every letter, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 1 million. Then I take my message. My message might be, meet me at midnight. So if I want to encrypt the M, here's an M here. I replace M with 17. E, here's an E here. I replace E with 8. I don't want to replace E with a number 8, because if I keep replacing E with 8, then it becomes obvious. So I find another E. Here's an E, that's number 10. I put a 10 here. T, that's a 2, and so on, okay? So every time I come to a letter in my message, I find a letter in the book, and I replace it with that number. And this code is almost unbreakable. Unless you can guess which book I've used, you will have no hope at all. Now, I could have made this code unbreakable. I could have just gone to my library and picked a book at random. And nobody would have been able to break this code. But I picked I didn't want it to be unbreakable. I wanted to give people a fair chance. So I picked one of my own books. Okay, I picked a book called Fermat's Last Theorem, which was my first book. And but I didn't number it from the beginning. Okay? Because if I numbered it from the beginning, if you have the Dutch edition of the book, it starts differently. It starts in Dutch. If you have the Swedish edition, it starts in Swedish. So I couldn't number it from the beginning. That would have been unfair. So I identified a part of that book which is the same in every language. Whichever translation you have, it's the same. I picked a part of that book that must be at least 217 letters long. And I picked a part of that book that's so famous that even if you don't have the book, you can find this passage on the internet. And if you apply those criteria, then you realize that the story of Fermat's Last Theorem is a French mathematician called Pierre de Fermat who solved a mathematical problem, but he never told us the answer. And he wrote in the margin of his book a message that was about 217 letters long. It's a message that's so famous that it's on the internet everywhere. And it's a message that was written in Latin. So whichever edition you have, you will have that Latin quote. If you don't have my book, then it's on the internet in 1 million places. So it's a very, very famous Latin note where Fermat says, I can solve this problem, but I'm not going to write down the answer. And if you take that piece of text and you number it up and you reverse the encryption, then the message just falls out very easily, okay? But nobody could figure that out. It took 6 months of work before one person in Cambridge figured out that decipherment. His name was Andrew Plater. And if somebody broke one of the stages, they would email me, and I would have a bulletin board, and I would have whoever was leading at that stage would be top of the board. And so Andrew Plater emailed me. He was right, so he went to the top. And other people, I would drop into other discussion forums, and other people were saying, well, how come Andrew Plater's so smart? How come Andrew Plater's ahead of all of us? How come he knows something we don't know? And this conspiracy theory began to develop. And the conspiracy theory was that Andrew Plato was in Cambridge, and I was in Cambridge for a while. Andrew Plato did his PhD in Cambridge. I did my PhD in Cambridge. And people began to figure out, then what's the connection? How, what did Andrew Plato have access to? And as a result of this conspiracy, for the first time ever, people went to the library in Cambridge and read my PhD thesis. They've never read it before or afterwards. So, but anyway, so that was stage 5. Stage 7 was again, 6 and 7 weren't as tricky as stage 5, actually, it turns out. But stage 8 is the one I was going to concentrate on, which is the Enigma Cipher. So the Enigma Cipher is famous for lots of reasons, but one of the reasons it's important in the history of cryptography is because here it is being used by the Germans in the Second World War. I think that's General Guderian, and here is a close-up of the machine. You can see it here. And the reason why it's so important in the history of encryption is that in the First World War, you have a revolution in communication. You have radio. For the first time, people can send large amounts of traffic instantaneously over vast distances. But on the other hand, other people can tune in their radio sets and listen to everything you're sending. So you have this technological revolution in being able to send data, but you need something to be able to protect that data. And so the Enigma was developed as soon as the First World War ended, really, in the years after. And not just the Enigma, there was a Swedish encryption device, there was an American encryption device. I have a feeling there may even have been a Dutch one. And people were trying to develop these technologies. But all of these companies went bankrupt, apart from the Enigma company, started by Arthur Scherbius. He was just about to go out of business, but then the German military machine began to gear up, and they wanted his machines in large numbers. And so every railway station, every army battalion, every U-boat, every airbase had to have one of these machines, okay? And the way it worked was a 3-person operation. So you can see here, you have somebody has the message in their hand, and he reads out the message. This person types it into the machine. Here's a keyboard there. Lights light up here. So you might type in hello, and the lights BVZQA might light up. He writes down BVQZA, he gives it to the radio operator, and then the radio operator sends BVQZA. At the other end, the radio operator takes down BVQZA, somebody reads out BVQZA, he types it in, and the lights hello light up, okay? That's how the machine worked. Now, I'm fortunate enough that I own an Enigma machine, and I'm fortunate enough that I managed to get it through airport security today, and it's here. And so, Yella, if we can switch to this camera. Oh, great. So, this is a genuine Enigma Cipher machine. It was captured in northern France at the end of the war by an American soldier. He was also a cryptographer, so when he saw it, he knew exactly what it was. And he just picked it up and took it back to America. And it lived in Texas for about 60 years. And this one was built before the war started. It was built in 1936. And some 80 years later, it's still working pretty well. So we can type in a letter. If I type in the letter O, the letter D lights up. Can you see a D light up? Great. Okay, you can see pretty much what I can see. So I type an O, a D lights up. If I type O again, A lights up. If I type O again, R lights up, and then H. So it's a pseudo-random letter generator. I'm typing in the same input, but I'm getting a different output each time. So why is that happening? Well, if we lift this lid here, you can see the lamps here, but more importantly, behind the lamps, you can see 3 rotors, 3 drums. And I can take those out. if I take the first one off here, you can see it's got 26 contacts. And on the other side, it's got 26 contacts. So when I type in the letter A, it goes in at the top contact. It goes A, B, C, D, E, F, G, back round to Z. Type in A, it goes in at the top. But it doesn't come out at the top. In the middle of these disks, the wiring is like spaghetti. So it goes in as an A, it might come out at B. It might go into the second one as B, it might come out as M. It goes into the third one as M, and it might come out as a J. Okay? So the scrambled wiring inside these rotors is what changes the letter. But on its own, that doesn't explain why the output keeps changing. Because if I keep typing A, it would follow the same electrical path, and you have the same output. I think I said the output was an M. But the reason the output keeps changing is every time you type a letter, this moves one step. So you type A, it goes in at the top, but that's a different contact. So it's a completely different electrical pathway. Type A again, it moves, goes in at the top, different contact, different electrical pathway, different output. So it is the dynamic nature, and when that does a full revolution, it kicks the middle one, okay? So it's the dynamic nature of the wheels that really causes the changing output. In fact, if I operate it with the lid open, then you'll see that happening. So I'll type O again, and you can see the first rotor move. Sometimes you might see the second rotor kick over as well. Every so often that will happen, but I won't wait for that to happen. But you can see that that rotor is moving, and that's the reason why the output keeps on changing. So that's how the encryption works, essentially. But how does decryption work? Well, if you want to decipher a message sent with the Enigma machine, you need to have the Enigma machine, but you also need to have it set up in the same way. Now, there are lots of ways to set up the Enigma machine. This wheel has got this axle has got 3 rotors. So I could move the rotors around to different permutations. So in this case, I have 3 objects in 3 positions. That gives me just 6 permutations. But then I can put them at different orientations. 26, 26, and 26. 26 cubed is about 17,000. Times the 6 permutations is 100,000. Now, where this wheel kicks the next one, I can change. Where this wheel kicks the next one, I can change. This one doesn't have a wheel to kick. But that's still a factor of 26 and another factor of 26. That's 100,000 times 26 is 2.5 million times 26 is 50 million. So this little thing here has 50 million different settings, okay? And then on top of that, I don't think you can see it very well, but just in here, there are some plugs. And what the plugs do is they swap letters around. So if I plug A with B, it means every time I type A, it follows the path of B. And every time I type B, it follows the path of A. And I can change the way those plugs are set up. And I think there are 20 plugs, so I can swap 10 pairs of letters. And that has 100 million different settings, okay? So the permutations here, the combinations here, are much, much bigger than the combinations here. But these don't change. Once you've plugged it, that's it. It's fixed for the day. Whereas this is continually changing. So it's really the large number of permutations here and the dynamism of what's going on up here coupled together is what gives you the security. But if you have an Enigma machine and you have it set up in the same way, then encryption and decryption is pretty simple. Let's try and send and decipher a message. Let me close the lid. If I just pick a simple setting, I could pick just 1, 2, 3 maybe. 1, 2, 3. Okay. Now, if I type the message OK, O gives me a S, and K gives me L. So OK is SL. OK, so you get SL, and you think, well, what does SL mean? Well, your machine has to be in the same position, so I'm going to move that back 2 spaces. 1, 2. Now, if I type in SL, I should get OK. S gives me O, and L gives me, you get the idea. So it's pretty reliable. Sometimes the contacts get a bit damp and they don't work. I mean, one of the nice things is if something goes wrong, like now, the wheels are moving, the keys are pressing down, the plug boards might not be connecting. So one of the things you can do is if you keep your finger down, you can do a walkthrough test. Now the wheels are not moving over, so nothing's changing. So that gives me an opportunity. So by typing the letter T, I know there's something wrong, so I can begin to investigate T a bit further without anything changing. If I think a bulb is broken, there's a nice feature. These bulbs are all original. These bulbs are 80 years old, and the spare bulbs at the top are all original as well. But if I think a bulb is broken, then I've got a battery tester here. If I think a cable is broken, I can test the cables as well. There's just nice contacts for testing cables. If I think the battery's flat, I don't need to change the whole battery completely. I just have an external power connections here, so I can just externally connect it to power and see whether that's the problem. So it's well designed in terms of troubleshooting and trying to figure out what's gone wrong. As the machine's open and as we've got it on camera, now might be a time if people have questions. I'm happy to take them now if people have one or two questions. You can just shout them out. Yes. How do they share the key? So every month there would be a piece of paper. And every line would be a different day. So today is the 15th. So it would say 15, pick rotors. I've only got 3 rotors here, but there may be 5 or 8 that you could choose from. So it might pick rotors 1, 4, and 2 in that order. Put them in orientations C, F, and K. Make the kickover points M and W. And this is the plug board settings. And if we're in the same network, we might be North Atlantic, or we might be North Africa. Everyone in our communications network would have that piece of paper, and every month somebody had to deliver that piece of paper. So you can imagine there were motorbikes going across the Sahara, and that's a huge risk. You know, that person may be hijacked, they may be a double agent, they may be just incompetent, but you know, the security relies on that bit of paper not falling into the wrong hands. And there were times when those bits of paper were captured and were then put to good use. And if you do capture it, you kind of want to capture it at the beginning of the month, not at the end of the month, although that's still very useful. Yeah. So why is it symmetric? Okay, so one of the things I didn't mention is it actually goes through the wheels twice. So I've missed out a few different things, but that's a very good point. This thick wheel at the end, it actually sends the wire back down a different path. It's called a reflector. So let's say it comes out the 3 wheels as an M. It will send it back as a P. And it follows the electrical wiring back again, and it might come out as a Q. But that means if you type Q, it goes through to a P, gets reflected as an M, and goes back as an A. So that is and that's a really crucial thing. I'll come to that a bit later, so thank you for that point. Maybe one last question, or I'll push on. I'll be around afterwards if people have other questions, and do come and catch me. But I'll just mention one other quick thing while we've got the camera here. If you were working at night, the risk was that the lights of the board might give away your position. So a sharp-eyed sniper might be able to spot where you are. So at night, they would often use, if they were working outside, they would often use this piece of just green plastic. So the idea is you just place it over the lamp board. And now if I type L, yeah, V has just faintly lit up. So This is there are a few of these machines around, but what's really nice about this one is that it's kind of got everything that it had when it was built, and all the serial numbers match and so on. So, but as I say, I'll at the end of the talk, I'll just need about 5 minutes to put it away, but if people have questions after that, I'll be at the back of the room. But let me carry on with the story quickly. So the story of the Enigma, here, this is maybe just a useful graphic for showing you how, well, if we can switch back to the PowerPoint, that would be great. Yella, if Yella's there. Ah, great, someone's onto it, great. Yeah, this graphic might help if I haven't explained it very well. Here's a 6-letter keyboard. That's what the rotor looks like. I type a B. The B goes in here. It goes up there, and it lights up as an A. Then this wheel rotates. So now I type B again. The wiring looks different, so it comes out differently. It comes out as a C. And in this one, you can see the reflector that I talked about a second ago. So you type in an A. There's the plug board as well. Here, the A is swapped with a B. And this comes through here, 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 gets reflected back down a different path and comes out, well, anyway, comes out as a C. So that gives you an idea of what the wiring that's going on inside the machine. Now, when the Germans first started using these kinds of machines, people thought they were unbreakable. The sheer numbers involved made it look like an impossible task to try and break the Enigma. And the French and the British and the Americans and everybody just didn't even bother trying. The only people who did try and break the Enigma before the war were the Poles. Because Poland, because of its geographical location with Russia on one side and Germany on the other, it knew that it was going to be in trouble sooner or later. So faced with such a desperate situation, the Poles tried to break the Enigma, and they made a very important decision, which was to bring mathematicians into code breaking. Prior to this, code breaking was all about linguistics, and you didn't see mathematicians or engineers or scientists involved at all. Although Charles Babbage worked secretly on code breaking. That wasn't known until about 30 years ago, because if you're a code breaker, you don't tell people, yeah? So there were scientists involved in it, but it wasn't very common and it wasn't very public. And the Poles were the first to say, right, we need mathematicians, we need lots of them, and we're going to try and break the Enigma. And they made significant breakthroughs before the war even started. And just before they were invaded, they smuggled out their ideas to the French. The French passed them on to the British. And before the war started, the British set up a code-breaking center called Bletchley Park. And they started, well, they had a great head start thanks to what the Polish code breakers had given them. And you can visit Bletchley Park. It's about a 40-minute train ride outside of London. And right next to Bletchley Park is the National Center, or the National Museum of Computing, which is also really, really worth visiting. They've got some terrific stuff there. And there's some silly rivalry between Bletchley Park and the National Museum of Computing, and they should really patch up their differences and be friends. But you have to visit them separately, unfortunately. But yeah, this is the code-breaking center at Bletchley Park. And this was the very first visit to Bletchley. This photo shows the very first visit by government officials who went there to Bletchley to see, is this place quiet? Is it secluded? Is it private? Does it have good communication links? Does it have space for adding new buildings? And after their visit, they were convinced that this was a good place to build a code-breaking center. And as the months and years passed, this became home to hundreds and hundreds of people who were dedicating their lives to trying to break not just the Enigma code, but other German codes and Japanese codes and so on. And I'll just speak briefly about how they broke the Enigma. So there was a message one day, a message was intercepted by a woman called Mavis Beatty. And she looked at this message, she was a code breaker, and she looked at the message, and the message was 200 random letters, because the output is kind of pseudo-random. But it wasn't quite pseudo-random, because in the 200 letters, there were no W's. Which is weird, because you would expect at least 5 or 6 or 10 or 15 W's. But no W's at all. And then she realized The only way you can have an output, a ciphertext, which is devoid of any W's, is if the input is all W's. Because if you remember from the question we had earlier, no letter can ever be encrypted as itself, because it goes through the three rotors, gets reflected back down a different path. If it goes back down a different path, it can't get back to itself. So no letter can be encrypted as itself. So if I type in W 300 times, my output will be everything except W's. So she'd cracked the code. She knew what the message was. 300 W's. Not the most interesting message in the world, but once you have the message, 300 W's, and once you have the output, which is what you have in your hand to start with, once you know the input and the output, then you can work out the exact setting of the machine, okay? Because normally you don't know the input and you don't know the setting, all you have is the output. And you have two big unknowns. Once you know the input and the output, then you can work out the only unknown, which is the machine setting. And she figured that out. She could then go back and decipher other messages that were sent that day. And one of the messages that she deciphered was about an attack on the British fleet at Alexandria. The British fleet were warned, and as a result, it was the first Allied victory in the Mediterranean, all because of this message being deciphered. Now, so the first question is, why would somebody send W 300 times? Now, the reason for that is, if you think, if I've got an unbreakable code, and I'm sending it across a battlefield, and you just can't break my code, you've got no hope. But what you can do is you can count the messages. And if you see I'm sending one message on a Monday, one on a Tuesday, one on a Wednesday, but 10 on a Thursday, then you know something big is going to happen on Friday. And that's called traffic analysis. And just by traffic analysis, you can begin to know what's going on in my head or what we're planning. So I combat that by sending 10 messages every day. And if my traffic is flat, your traffic analysis is no good. So when somebody sent 300 W's, they were probably just maintaining their quota for the day. Yeah? If they'd sent a random message, it would have been fine. But they didn't. They sent something that was utterly predictable or deducible. So that worked once, but it wasn't something that you could rely on. What Alan Turing did, what his great contribution was to say that with a lot of messages, you can't guess what the whole message is. You can't guess it's 300 W's, or you can't guess the whole message. But even if you can guess part of the message, maybe that's enough. And you can often guess the part of the message. The way the message starts may follow a certain format. If the message arrives at midnight, it might begin with 0000. If the message comes from over there, and we know the Germans have a weather ship over there, then we may be able to guess what terms they're using to describe the weather in that part of the ocean. So Turing's great breakthrough was to say, even if we can guess a bit of the input and match it with a bit of the output, that will help us work out the settings of the machine. And he built machines called bombs to help sort this out. And as a result of his work and many other works and many other breakthroughs, it came to the point where the Bletchley Park codebreakers were deciphering messages almost as quickly as they were being read by the German military. And I think it's almost, gosh, it's 10:02. Let me just wrap this up fairly quickly. I'll just make 2 or 3 points before I finish. As I said, it was Alan Turing who broke the Enigma, working with many, many other people. And Alan Turing never got any credit for his work, and he took his own life in the 1950s because of his sexuality. He was being hounded by the police and by the government security forces as well, to some extent. But he never got the credit for his work, and neither did many, many other people. And people often wonder why didn't, Enigma, the breaking of the Enigma was kept secret not just during the war, not during the 1950s, not just the 1960s, but it wasn't until 1973 that the story of Bletchley Park began to emerge. So people often wonder, why was this kept so secret for so long? And the reason for the secrecy was that as the war ended, the Allies captured lots of these machines. Now, this machine was captured, and many, many others were captured, and they were brought back to London, and they were kept in the government offices in central London. And the government civil servants, the government workers, would ring up other countries, such as Australia and Canada, and they would say to these friendly countries, they would say, look, you're our friends, and we've captured lots of these German machines, and the Germans say they're absolutely unbreakable. Why don't you have some? So the British were giving machines to their friends because the British knew they could crack these codes, okay? And so the British could spy on their friends in the 50s and in the 60s. And that's why this was so top secret for so long. I'll just wrap up the story of the Cypher challenge quite quickly. Stage 10 of the challenge was an Rsa Cipher. These are the Swedish code breakers who cracked the code, cracked all 10 codes. And stage 10 was obviously the hardest one, and it involved RSA. So you had to factor a very, very large prime number. And it was pretty much the biggest number that had ever been factored. It wasn't much bigger than the record. So I knew that people could factor this number if they tried, but it would be really tough. And they came up with some new ways of implementing factorizing software and did some really clever things, and they factored the large number, and they could break the RSA. Actually, if you deciphered the RSA, that gave you 2 keys. And with those 2 keys, you could undo another code called triple DES, okay? So let me just tell you what triple DES is. So DES was the data encryption standard. It was a form of encryption that was developed in the 1970s in America, and it was kind of the standard form of encryption that was kind of shared around the world. But then DES became weak by the mid-'80s probably. And so DES was replaced by triple DES. So with triple DES, you apply DES once with 1 key, and then you decrypt, but you decrypt with the wrong key. You have a second key, so you decrypt with the wrong key, so you make it even more encrypted. And then you re-encrypt with the first key just to get it in the right format, okay? And that's triple DES. And this is unbreakable. You will never break triple DES, or nobody at the moment can break triple DES. But you didn't have to break triple DES. What you were supposed to do is factor this large number, undo the RSA. The RSA would give you these 2 keys, key 1 and key 2, and then you could undo this very easily, okay? But the factoring was a mammoth task, okay? But this was impossible unless you did the factoring. But when I went to Stockholm, when they won the prize, I went to Stockholm to give a talk on how I made the codes, and they gave a talk on how they break the codes, and I gave them the check for £10,000. But during their lecture, they revealed that I'd made a mistake, okay? And my mistake was that when I did the triple DES, okay, triple DES, remember, you encrypt with 1 key, you decrypt with the wrong key to make it even worse, you re-encrypt with the right key to get it in the right format. What I did was I encrypted with the first key, and then I decrypted with the first key. And then I encrypted with the second key. And that's only single DES. And that can be broken in about 2 hours, okay? Now, luckily, they didn't think I could be that stupid. So they didn't try this approach until they'd done the factoring, which took them about 3 months. And then when they did the factoring, they realized that I'd got this completely wrong. And I suppose that's a really important message, is that, the encryption systems that we use today, and Sven mentioned it today, that without them, a lot of the technology that we use today, a lot of the companies that are successful today would just fall apart. And we rely on this effectively unbreakable form of encryption that's often used in so many places. But if it's not implemented properly, and if human error, like the 300Ws with the Enigma was actually a very strong machine, and often the way Bletchley broke it was by people doing regimented starts, or predictable ends, or predictable time checks, and so on. So whether it's Enigma or whether it's Triple Des or whether it's me and my Cypher challenge, often it's the human error that leads to the undoing of these codes. If people, I think I took questions during the talk, so we probably don't have time for questions now, I guess. But if people if people do have questions or want to come and chat, then please just give me about 6 or 7 minutes to put this away, and then I'll be at the back of the auditorium. But thank you very much for inviting me to speak. Thank you.